Hi, my name is Shane Zhao. In this video, I'm going to talk about ZipLine, an optimized algorithm for elastic bulk synchronized parallel model. So let's look at the background of this elastic bulk synchronized parallel model. It is running in the parameter server framework. The parameter server framework is a centralized data parallel distributed platform for deep neural network model training. It follows the iterative convergent optimization. Let's look at the animation example here. We have a data set, and data set is partitioned equally based on the sizes or the number of workers. Here we have 3 workers, and we have 1 parameter server. The parameter server will send a replica of the training model to each worker. Then the worker will train the model based on the data it received from the dataset. Then it will compute the gradient. Then the gradient will be sent from worker to the parameter server. The parameter server will aggregate all the gradients, then do the weight update. When the model is updated, the new model will send back to each worker. That completes an iteration, and the new iteration will start. Now, the problem for distributed training is the synchronization cost of workers, such as the faster workers has to wait for the slower workers. If we reduce the synchronizations, that will decrease the waiting time and also increase the iteration throughput. That could lead to fast convergence. However, this fast convergence may end up in a low accuracy, and that is because reduced synchronizations will produce a lot more stale gradients, and these stale gradients will be updated to the weight iteratively. And then how to balance between the fast convergence and the high accuracy is still an open question. Previously, there are 3 most relevant approaches to handle this synchronization problem. They are called the BSP, SSP, and ASP. Bulk synchronous parallel, BSP, as its name suggests, is synchronized for all the workers at the end of each iteration. That is, all workers have to wait for each other, tell the server, aggregate all the gradients, and then update the weight, set the new weight to each of them. Then they can proceed to the next iteration. And that triggers a straggler problem. That is, say in here, worker 2 is straggler. It takes longer time than worker 1 and worker 3. Still, synchronous parallel, SSP, tries to alleviate the requirements of BSP, and then it's only trying to focus on the fastest and the slowest worker. In this example, worker 1 is the fastest, worker 2 is the slowest, and it allowed the fastest worker to run 3 thresholds, 3 more iterations than the slowest worker. Then it has to stop when the threshold exceeded till this worker 2 reach the end of iteration, then it can proceed. In asynchronous parallel, all the workers are computing the gradients independently. There's no synchronizations among the workers, so it will deliver the maximum iteration throughput and also produce the largest number of stale gradients updates to the model training. Our method is built based on bulk synchronized parallel, BSP. In this example, we have BSP, and for all the workers, they have to wait for each other at the end of each iteration, and we call this a super step. And then the barrier means the synchronization happens here, and the server will aggregate the gradients, update weight, and send them back, and then a new super step will happen. So, similar to BSP, we also relax the requirements of the BSP. In each super step, we define that all the workers can run more than 1 iterations. And between each super steps, each worker can have different steps. Say in super step 1, worker 1 has 3 steps. While in super step 2, worker 1 has 5 steps. That means each step, they still send the gradients to the server, but server doesn't do synchronization for all the workers. And the synchronization only happens between the super steps. So you can also consider all the workers in each super step, they are running ASP. When the barrier started, we switched back to BSP. And our goal is to find the barrier which will yield the minimum waiting time among these workers. The intuition about how our approach works is as follows. Assume we have 3 workers are running in BSP model. Initially, once each of them finish 1 iteration, they have to wait for each other. And then the barrier started at worker 1, then and worker 3, worker 1 wait for the worker 2. Waiting time is this much, highlighted in red. And then the dashed line is the end of the barrier. Then we think, wait a second, what about we allow this worker running more? And let's simulate, or let's estimate the R future iterations for each worker based on the information we just got. So then we can go search what will be the minimum waiting time among these our future iterations. And in the end, we will find this green barrier, which yields the minimum waiting time. And that is our elastic BSP. The parameter server can always tell each iteration of each worker. For example, when the worker 1 finished one iteration, it will send its readings to the server, and the server will basically know the timestamp. Based on the timestamp, it finished one iteration. And then in another iteration, second iteration, third iteration, server can always tell. Now we assume that we already know the future iterations by estimation, and then we obtain this kind of matrix. Each row is all the workers we have in the cluster, and then each column are the iterations or the end of the iterations for each worker. Then we can map this iteration or timestamp into a one-dimensional line, and then we use different color to color each worker. So the timestamp are distinguished based on either their timestamp value or the color value. Then our optimization is transformed into this color-looking problem, where we are looking for a set that contains unique color that includes all the workers, and the range, and the range should be the minimum. That goes to the details of our ZipLine algorithm. So as we see earlier, that we have this line of time points with different color. So what we do for the ZipLine is we first initialize with a set. This set has range D1, and then we define this D1 as our optimal set. Then we scan through each data point till the end. Note that when we add a new element or point to the set Z, we have to remove the same color out. Say we add this red dot in, we have to remove the previous red dot out. In this manner, we have to scan one at a time. Now we find a new set with range D6, and we find out D6 is smaller than D1. And then we will remove this D1 set and keep this D6 set as the optimum. As it continues, the ZipLine finds another set with range DU10, and the D10 is equal to D6. However, here we are not going to update D6 with D10. And in this work, we also proposed the optimized ZipLine algorithms named ZipLineOpt and ZipLineOptBS. The ZipLineOpt basically optimized the add operation of the scanning set Z, and it's used pruning to skip the search time of adding new elements to set Z. That is, to skip the search if the new elements has the same color as the leftmost element of Z. Let me give you an example. Here we have ZipLineOpt used over here, and we add the red dots into the set Z. We will check the leftmost point. Is this red? If it is, we're not going to scan through the D to find the same color, since the last one is the same color. Then we add this red in, remove this red out. Then the second method is called ZipLineOptBS. It simply basically further optimized add operations. It uses the matrix containing the information of the data points that allow us to do a binary search in this set Z. And where we get the matrix, as you see in the previous slides, we get a matrix where each worker is the row of the matrix, and the column is each iteration of the workers. And those iterations are like the future iteration. Here's the example of ZipLineOptBS. And then when you can see that when we want to add this blue diamond into this set, and this blue diamond in the existing set is somewhere between the last and the first element, that will require us to do a iterative search that costs O of n. And with this binary search, that is, we can use the matrix information to locate the timestamp of this blue diamond dot. Then we can use binary search to find it. We compare the ZipLine and its optimization methods on their computing time as a function of the number of workers, that you can see from 0 to 1000 on the x-axis. The y-axis is the computing time, and r is the future iterations we generated during comparison. And you can see that when the r is small, the future iterations of all the workers is small, the difference is not that much significant. But when r becomes large, we can see that the ZipLineOptBS is very fast. Then the ZipLineOpt is the second, and the ZipLine, the original one, is kind of slow. We also like to address that when the number of workers is less than 150, and we can see that the ZipLineOpt is doing better than the ZipLineBS. The ZipLineBS is the orange color, and the ZipLineOpt is the green color. And that is because the ZipLineBS uses the matrix for information retrieval that costs extra time. However, when the number of workers increases, that also means the number of data points increases, and those operations, the information retrieval at cost, can be amortized to many operations here. And finally, we run our ElasticBSP on network called VGG16 based on the ImageNet 1K. It's running on 4 workers. And as we can see here, our ElasticBSP with different R, the feature estimations, are running better than the BSP. And they are still learning. They are not really converged at this point, since we only run for 24 hours. However, we can see that the learning speed of ElasticBSP is 1.77 x-fold faster than BSP. And then we also add the other parallel model like DSSP and SPASP in comparison. And then we found out that they are very hard to learn this complicated DNN on the large data set. In this video, we introduced ElasticBSP It provides faster convergence to higher accuracy than BSP. We also introduced ZipLine, the algorithm that finds the optimal waiting time for synchronization. It is a greedy one-pass algorithm. We also introduced the optimized version of ZipLine called ZipLineOpt and ZipLineOptBS. And ZipLineOptBS is the fastest among them. It has the linear arithmetic time complexity. Thank you for watching.